So good afternoon. Let's get back to our discussion on the time-dependent perturbation theory. We do it for one purpose. We would like to see how we can obtain the key results related to stimulated absorption and stimulated emission in simple quantum mechanics. There's a third process called spontaneous emission, which look very natural and simple. However, within Schrödinger quantum mechanics, we need to do a little bit more before we can get a quantum mechanical formula for the transition rate, how fast a spontaneous emission would occur. So that's the plan for our progress. So let's see how far we can go. Just recap the most important result in Tuesday's class. We developed the first order time-dependent perturbation theory. The question was, I have an atom. Initially, it is in an initial state that I call 1. And then a time-dependent perturbation term, interaction term kicks in at some time called 0. And then we want to ask, what is the probability amplitude that the atom will be found in some other state called 2, that is the final state, after the perturbation is switched on for a time duration t. So we use the time-dependent Schrödinger equation and then do a few steps. Actually, every step is elementary, nothing fancy. And then we get at this particular key result. It is related to 2 integrals. One is spatial. So we have an initial state of the atom. We know it is an energy eigenstate. We have a final state of the atom, which is also an energy eigenstate of the atom part. And it is the interaction part. Last time we also discussed the particular form of electric dipole mechanism that we are interested in. It has the atoms, the electrons in the atom's coordinate coupled with the oscillating electric field of the incident light. So it has some spatial part, coordinates of the electron in it. And we understand that it is this interaction term that could lead to transition from the initial state to the final state. So this is a spatial integral, and it will determine, later on we will see today, the selection rules. In addition, there is a time integral. We are interested in the effect of the perturbation switched on from time 0 to time t. We integrate over this time duration to see how that perturbation could lead to a transition to the final state. So therefore, there is a time integral involved. There is a time factor that has to do with the energy difference between the 2 levels, as well as there is a cosine omega t prime due to the incident light. So altogether, there is a time factor here, and there are 2 time factors here, for which we should do the time integral. So this is the key result. After we get this, take this thing square. This is complex, so take this square. That is the probability of finding the atom in some final state number 2 at time t. So that is the key results that we will be applying to understand transitions in atoms. So last time, I make use of this electric dipole term, plug it in. So last time, we understand that it is of this form, and then plug it in, and explicitly, there are two integrals, a spatial one that has to do with the position of the electron in the atom. So that is the matter. And then we have this temporal integral that has to do with the incident light frequency, as well as the difference in energy of the initial and the final state. At this point, it is important to realize that what we have been calling initial is just one, the initial state one. We haven't said anything about the final state two. It could be above initial state. In that case, it will be an absorption. Or the formula works also for a final state that is below the initial state, in which state it will be an emission. So up to now, our formula works for both stimulated absorption and stimulated emission. So that is what we did last time. So let me pick the discussion up from equation 11, and then we will focus on, we have an atom. What does this term, term number one, the left-hand side, say about selection rule, and what does the second term say about this H bar omega? The incident light must hit the particular energy difference of the two states. Both are common sense, but it is, I think it is the first time you see this common sense coming out quantum mechanically. So let us pick up the atom discussion. So this is exactly the formula that we wrote down from the time-dependent perturbation theory. So here, instead of initial 1, 2, I use initial final, but still, initial is somewhere. The final could be above or below. It doesn't matter. We haven't confined ourselves to any particular situation. And this spatial times temporal integral, this form of writing the result out is particularly illustrating. Here we see that it has to do with a particular integral of the atom. We have some initial state, position of the electron in the atom, some final state. So for example, hydrogen, we can look up what this integral wave functions are and then try to do this integral. Some of the integrals may be 0, then you have no chance of finding the atom to go from that particular initial state to that final state. So you may have heard about this before, called forbidden transition, not allowed. But if this is not 0, then this transition is allowed. But now you know a lot more. Even this integral is not 0. Sometimes it is big, sometimes it is smaller. That will be reflected in the intensity of the spectral line. That line will be brighter. If this integral is bigger, that line will be dimmer if this integral is smaller. Okay, so we are getting at something very real. So this is really applied quantum mechanics in essence. The second integral is also very interesting and important. It has to do with the atoms' difference in energy and the light incident light frequency. So we will work on these two parts on the pages to follow. So let's look at the temporal part. The E field has an amplitude and an oscillatory time dependence, cosine omega t prime. This omega is the angular frequency of the incident light. Remember that cosine omega t can be written as 2 exponential, but one with a plus sign, another with the minus sign together. Okay, so this is the most illuminating step. Now, if you put this thing into here, the temporal integral actually has 2 time integrals. One has to do with the plus I h bar omega t prime. Another has to do with the minus I h bar omega t prime term. Okay, so we have 2 different terms. Now these 2 different terms have much physics in it. If you are not interested in mathematics, now pay attention. It is physics time. We can do this integral explicitly. It is one of the elementary integrals you learn, integrating EIX dx. Okay, so it's the simplest, or EX dx, that is the one of the simplest integrals. We can do it, and we will do it. But at the outset, think about what happened, right? Now, for reasonably long time, if t is reasonably long, I will explain what is long later. Physically very short, but mathematically it says if it is long enough so that this thing keep on oscillating. Now it is oscillating, right? So if you give it time to oscillate, you integrate over an oscillating thing, right? Usually it is 0. All right? It works for both cases, except in one situation. If this thing is 0, the whole integrand is 1. In that particular case, the integral is not 0. All right, so let me summarize. For the first term, only if the exponential thing is 0, that means initial minus final is the incident h bar omega, except this particular case. Otherwise, this term is 0. Okay? Now, for the second term, same argument. Only when this is 0, that is to say, final is above initial and the difference is equal to your incident h bar omega. Otherwise, if it is not such condition, this thing is oscillating, you integrate over reasonably long time, is 0. All right? So we started to see 2 processes. For the second term condition, final is above initial, that is absorption. For the first term, the only condition that we should consider it is when the initial is above the final and equals to the incident light. That is emission. All right. So we started to see rather profound physics actually. From this perturbation term, cosine consists of two terms, and then there are two integrals, and we already recognize or get a sense, physical sense. The first term has to do with stimulated emission because there is incident light. Stimulating means there's something incident. 搞緊佢，係咪? So it is a emission condition. The second term is absorption condition. Okay, so I want to pause here. If you have any questions, we see some physics. One term is absorption, the second one. The first term is emission. Do you get the point? Any question? Because afterwards, we will just play with the integral and see what additional physics comes out from the integral. Understand? So let me move on. In fact, we can do the integral, right? This is just integral e to the x dx. Well, chain rule, you do something, okay? So this is the answer. As we already discussed, this term will be responsible for absorption. The other term will be responsible for emission, okay? And here comes another argument that we need in order to move on. At the end, what we need is the probability, right? So for those who don't think in terms of physics, you may say, I just do this square and then I will get 4 terms, very happy, things like that, okay? But we are doing physics. So the argument that follows is, when I have an initial state, if this term is important, that is to say, if the final state up there has a difference that is h bar omega, so when this term is important, this term cannot be important. In fact, if this denominator is close to 0, I think this is like 2h bar omega. Okay, so the argument is very simple. When this is big, this is small. And when this is big, this cannot be big, this must be small. All right, therefore, it is legal to single out the absorption term and then work with it to get at the absorption probability, and then work with the first term and ignore the second term to work out the stimulated emission term. We will work on this term one by one. That is to say, we don't worry about interference term. We need not, basically, okay? So this is another argument after the integral one. So the next step, we will focus on this term and then work through the absorption probability. So we will work on absorption. That is to say, we single out the second term. All right, here. Okay, so when you have a second term, there's a standard step if you don't want to play with the exponential. I think you have done this in some other course. So the trick is pull out half of this. Okay, so you factorize half of this, therefore you will have half of this left, and then you have to minus the same thing, but with a minus sign here. Okay, therefore you will pick up a sign of this thing divided by 2h bar. So this is exactly what I did here. So you pick up a sign. There is a over 2 that cancels out. There's a 2 that cancels out the 2 here. All right. So therefore, I also pick up an I, but it's not going to harm us. We will take this square. Okay. So this is the second term after I pull out this half of the exponential. This is exact. All right. I just don't want to play with exponential. I like sine cosine thing down there. Okay. Now we can get an answer in one step. We just take the a2 square. So take this thing square. We don't need to worry about I anymore, etc. So remember, this is a integral. Some final state, Z of the electron, initial state. This. The wave function can be complex, therefore, this Z matrix element is in general complex. When we do this absolute square, it becomes this complex quantities square. And then we pick up this square of this, and then the energy factor denominator square. And this thing, when we take the absolute square, is a 1. So we have a 1 here, invisible. So the box 17 is the answer in the quantum mechanical, in answering the quantum mechanical question. If the atoms is in some initial state 1, what is the probability it is at some final state 2 at time t, after the incident light comes in at time equals 0? Okay, so this is a key step. All right, now it is absorption very obviously, because it will be big when E1 is down here, E2 is up there, and when the incident light h bar omega hits the difference. Okay, so we want to further develop the answer a little bit, but all the physics about stimulated absorption is here. There are 2 levels of understanding to go with the answer. Baby level, basic level, okay? So the baby level is understand that there are 2 conditions that will fill in your knowledge. You know the conditions in previous studies very well, but now you have the quantum mechanical backup for the 2 key results. First, we have to check whether this integral is 0 or non-zero. If it is 0, then you don't need to work anymore. This transition from this particular initial state to the particular final state, you pick a 2 and then you do the integral. If this is 0, it is a forbidden transition. This is not allowed within electric dipole mechanism. So this will give you the selection rule. So this is baby level number 1. Baby level number 2, you look at this condition, you know, I must buy a night source. The omega is the right omega between the initial and final state that I want to plot. Well, it's common sense, right? That's what Bohr told you in 1913, Bohr model, right? From some level, down level, the light will be given out or absorbed. So this is the baby level understanding. So that's what I said, common sense. But now it becomes quantum mechanical common sense. A higher level study will be, it is not 0, all right? Can we calculate how big it is? So it gives selection rules as well as the brightness or dimness of the spectral lines. Developing it further, basically, even if you buy a laser, there is a narrow bandwidth, so it may not be right on resonance. What if you have a group, although narrow, a group of incident light hitting the atom? That is usually the case. And then in this case, we can derive further to get something called the probability per unit time of an atom absorbing the light and make a transition to the excited state. Even further development is that you have an excited state, but you may have a group of final states. This is usually the situation in solids. Because in solids, you have energy band. So-called energy bands are, you have Schrödinger equation solutions. The energies, they are densely packed. Therefore, from one initial state, even you give me a h bar omega, there are quite a number of final state for possible transitions. Nonetheless, all this higher level understanding can be worked out based on equation 17. All right, so we will try to develop a little bit further, but we will not do the group of final states case. In order to proceed further, let's consider the time factor. So where did I get this? Here. Okay. Now this is a complicated function, so pay attention. Try to get your understanding once and for all. I say that it's complicated because there are different viewpoints to look at the function. To be explicit, this function can be viewed as a function of omega as well as a function of t, because you really have something t here. Okay, now for the discussion on this page and the next page, let's focus on f, this capital F function, as a function of omega. That is to say, I'm thinking about a particular snapshot in time. So this figure is for some fixed time t. So I take t as a number, and then I have omega left. So I would like to plot it as a function of h bar omega. So notice the axis that I circle out. All right. Now, in order to make the x-axis carrying no unit, we are plotting it as h bar omega divided by the energy difference. So I have an atom, initial state, final state now is above it because it's absorption term. So I take this as given, and this figure, the x-axis, means the following. I am going over some h bar omega. I'm sweeping some h bar omega through different values. Okay, so the x-axis is going from smaller h bar omega to higher, hitting the right number, and then even higher. Okay, understand? So now let's look at the structure. 1 here means the h bar omega is equal to the energy difference E2 minus E1, and that is the 1 there. So from smaller, less than 1, to above, to hitting at the right difference, and then above it, f of omega is of this form. So it is slightly oscillating, but very small, and then it will hit a peak rather sharp, okay, and then come down again, oscillating a bit. So this is the function f of omega. All right, now let's analyze the feature in more detail. This is not easy, but try to focus for 3 minutes, and then you will get this thing, understand once and for all. Let's look at how the peak value here behave. I hope that you know sine x over x, x goes to 0 is 1. You know that, right? You know some calculus in year 1. So if you use that, it is easy. You just fill in some term here. So I divided by 4h bar square, and then times 4h bar square, there's nothing. And also if I fill in a t square, so it's also a 1, everything canceled out, right? But then for the thing here, when h bar omega hits at the difference, this will be 1. Okay? Therefore, the peak value is this value. Oh, understand? Okay, so nothing fancy, just use your skills. So this peak, once time is fixed, sometime t, it takes on the value this. All right, now second point, where is the zeros? The first zeros, it drops. Okay, now the first zeros will be sine of this thing is no, when this argument is like sine theta, okay, when this argument is plus pi or minus pi. Okay? If this is the case, this function will be 0. Do you understand? Okay? Therefore, you can work out what are these 2 points. The first zeros from the peak, boom, come down. Okay? At least you see that the first 0 goes like 1 over t, because you have a t there. Have to subtract over. Okay? So the second point, the zeros on both sides deviate from 1 by 2 pi h bar divided by the energy difference of the atomic states and 1 over t. Similarly on the other side. Okay, so let me summarize. This function, if I look at it as a function of h bar omega or omega, it peaks at the resonance. So you have a difference that gives me, it hits at the energy difference. The peak value goes like t squared. But why is this sharp peak? It goes like 1 over t. Okay, do you understand? So roughly speaking, do you see that the area under the curve goes like t? Okay, questions? You understand? Okay. Any questions? Okay. So now, so is this the peak that will become sharper and sharper? That's exactly true. So one student pointed out that he's asking, will the peak become sharper and sharper as time is longer? The answer is a big yes. Okay. So you can think about it. I can draw another picture at a slightly later time. The peak will shoot up. The 2 sides will squeeze in. Okay? But the area under the curve just goes like t. All right? That is important. That will become important later. So if that is okay, I don't need to go through this page. Okay, this is for those who need some help in mathematics. This is what I did. And if you don't like the x-axis being this, fine. This is the picture for the x-axis simply as h bar omega. And then you must hit this difference. Okay? Now, there are some books, when you read on this topic, there are some books look at the same function and view it as a function of t and draw what happened in t. So pay attention when you read different things. There's also some other books, when they discuss this function, do the following thing. H bar omega is a constant. And consider, so you have an h bar omega, and then consider the energy difference of the 2 states being changing. Okay, so there are many different ways to discuss the same function. But at least if you know one case very clearly, then that helps. So let me summarize. As time goes on, slightly longer, the peak will be higher, the 2 sides will be narrower, and the area under the curve will go like time, first power in time. In fact, we can work out this mathematical form step by step, but I hope it is already enough to convince you that as time goes on, this function goes like t, because the area under that peak goes like t, and it is a delta function picking up the right omega. So h bar omega must be equal to that difference. Because of the prefactor that I factor out here, erased that. So the prefactor that comes out is 4 things like that. I have this prefactor. Okay, so what I want to say is the following. By drawing picture, I hope I convinced you that because for a delta function, you integrate over things, it is the area under the delta function. And now we know that it has to go with t, so it's a t in front, and it is a delta function. So we will be using this a bit later. Okay. I would like to discuss a little bit, because some of you may be too mathematical. And think we need 1 hour as a long time and things like that. But in fact, it's not the case. So we work out that there is something E2 minus E1. Okay, and it is to be compared with h bar omega. All right, and then it is, you see this kind of factor. Okay, now the point is that for absorption in atoms, for example, the familiar one you have seen in your previous lab is the sodium yellow line. Sorry. So yellow is visible. So visible the frequency is something like 10 to the 15. Okay. And then, therefore, this is 1/2. Right? And that corresponds to 3s, 3p. How can I erase it? I need to get my pen. So quite similar to hydrogen, 1s, 2p. Okay. So you have this yellow thing. It is 1/2. So a characteristic time is 10 to the minus 15 second. Okay, so this is basically saying that this difference, that is omega 21, that sets a very high frequency scale, therefore a very short time scale. So when we are saying that we need so-called long time, to see the sharp peak, this long time is long compared with this kind of thing. So anything is long, okay? Let me see how to get out. Okay. So we are done with a big part in absorption. Then the next few pages are easy. Now I play with the emission term. So I go back to this general equation. We discussed that when this is big, this is small. So we only consider that term for absorption. Now we go to this term, when this is big, the other is small. So we pick this term out, and then I'm a bit lazy here. I just do the same thing. You pull out half, you get this. The only difference is this E2 minus U1, this plus sign. Okay, you also pick up an I, but it's harmless. You take the square probability, you get the same thing. So this is the same function, right? With a difference in sign. Then you know, when I plot this thing, it's also, you must hit that right energy difference. However, it is our initial state called 1, final state called 2. So our incident light, omega is always positive. You don't have negative angular frequency in light. So we need the final state to be lower than the initial state, thereby this is emission. So we got stimulated emission in one shot together with stimulated absorption. That is to say, within Schrödinger quantum mechanics, you get this, so some mysterious process, stimulated emission, free of charge. You try to understand absorption, you also get emission, okay? But it is stimulated. It is stimulated because you have the field square here. This is the field intensity. The stronger the field, this probability is higher. So it is stimulated emission. This is Schrödinger. Einstein proposed this term earlier than quantum mechanics in 1916. We will discuss that a bit later. So let me summarize the two processes that we have so far. When we simply label the two states 1 and 2, like this way, now I'm thinking about 2 is the higher one, 1 is the lower one, okay? And then we can think about the same two states. For absorption, this is initial, this is final. For emission, this is initial and that is final. So I'm fixing these two states and I simply call it 1 and 2. Therefore, I can copy the formula out and translate it to this definition. I'm not fixing the initial one to be called 1. I just call this 1 and 2 by it is being higher in energy and lower in energy. So in this case, the absorption one, I don't need to change anything. But for the emission one, I have to go with this idea. So I will have the higher one minus the lower one. And then if that hits the right frequency, I will have stimulated emission. So I'm rewriting the two equations using this new labeling. Now immediately you see something. Look at this integral. This integral has to do with this particular two states and with a Z in the middle. The first one, I have the first term. I have the lower energy one on the left-hand side. So this one, okay, is psi 2 star Z psi 1 d over all volume. Now this one is psi 1 star Z psi 2 d over volume, in over volume. Okay. Now, obviously, they are related, maybe with an I or a sign, doesn't matter. Okay. The whole point is that both are square. Okay. So therefore, we have the following observation from quantum mechanics. If we have two states, there's some light in there. Depending on whether the atom is down there, it may be absorbing, or up there, this light will stimulate emission. We know one thing. When we consider this probability at time t, the absorption probability is the same as the emission probability. Okay, so this is summarized down here. This is a quantum mechanical result. Later on, we will have a discussion on Einstein's famous work proposing the stimulated emission process before quantum mechanics was established. In his analysis, he also get this result, the one that we highlight here. So it's rather magical. But here we get it step by step. Okay. So let me pause here for a break, and then we will collect some physics results, selection rules, why we have those selection rules, and then how we get something called transition rate per unit time. What is the probability that there's a transition? Okay, so those are measurable quantities, and that is also related to something called the lifetime of an atomic state. You know, high-level states are unstable, but how long they will retain there before they come down by themselves. Okay, so let's take a break now.